All right, so we're skipping section 10.1, and we're jumping into 10.2. 10.1 is conic sections. So we're not going to work on conic sections. We're just going to jump right into parametric equations. And usually coming after finishing with sequences and series, parametric equations are a nice kind of a nice break from the kind of thinking that we did with infinite series. But so far we've been working with equations where one variable is defined in terms of is a function of the other. So we have y as a function of x, for example. When each of our variables x and y is a function of a third variable, we call a third variable parameter, then we end up with a parametric equation. Some pretty standard examples of parametric equations are projectile motion, where you have x in terms of x as a function of t and y as a function of t. So it's t time is our parameter, and for any specific time we can find a value for x and y. So that's a standard example of a parametric equation. We'll use parametric equations in several different contexts, but that's kind of the classic example. The path, if we're describing motion in terms of parametric equations, or we're graphing parametric equations, we call the graph a plane curve. So if we graph a parametric equation, so just so you understand, or you're familiar with the terminology, and next semester we'll talk about space curves. So our equations, so we have a couple of functions. F and g are continuous functions of t. On some interval. Where t is our parameter. The graph, the set of points x and y is called the graph. So we're just talking a little bit about our terminology. So we call the set of points x and y as the graph of the equations. And the graph along with the equations, just so we have this terminology clear. So the graph with the equations is what we call the plane curve. So we need the two together to talk about a plane curve. And it'll come up again a couple of times in terms of how we define the curve and what we're actually talking about. But I just want you to be familiar with the terminology when we talk about a graph, when we talk about a plane curve, what we mean. And usually we call the plane curve C for curve. So the book will use the terminology plane curve. It'll talk about the graph. It'll talk about the equations. So I just want you to be familiar with that. Sometimes the terms graph and plane curve and set of equations, the parametric equations, are kind of used interchangeably. But there are a couple of times when this distinction does become important. A lot of times we just use them interchangeably. So what we're going to do today is just do some basic work with parametric equations. So if we want to sketch a the graph of a set of parametric equations, a lot of times we have to eliminate the parameter to figure out to come up with a familiar equation to make a sketch. So eliminating the parameter is going to be one important tool that we need to work with parametric equations. So if we have a set of parametric equations, let's say we have x equals t minus 1 and y equals 2t squared minus 4t plus 1. We want to eliminate the parameter and sketch the graph. And let's say our domain for our parameter is restricted to 0 less than or equal to t, less than or equal to 2. So we're given this set of parametric equations. We want to know what the graph of this set of parametric equations look like. So to eliminate the parameter, all we do is solve for the parameter in terms of one of the variables. So here it looks like it's going to be easier to work with this equation. So from this equation I can say that t equals x plus 1. I just solve one of the equations for the parameter, and then I substitute. So I get y equals 2 times x plus 1 squared minus 4 times x plus 1 plus 1. And when I simplify this, I get y equals 2x squared minus 1. Now my domain for t was 0 less than or equal to t less than or equal to 2. I need to adjust my domain because here my domain is in terms of t. For my graph I want the domain to be in terms of x. So if t is between 0 and 2, what is x going to be between?
Negative 1.
X is going to be between negative 1 and 1. So I'm just using the domain on t to figure out my values for x. So this is my rectangular equation. This is my domain for my rectangular equation. So now we can sketch our graph. So what is this graph going to look like? What's that? Let's see, it's going to intercept the y at negative 1. So we're down here at 0, negative 1. And then when when x equals 1, y is going to be 1. So we have a point up here at 1, 1. And when x is negative 1, we have a point at negative 1, 1. And what kind of curve connects these? Parabola. So there's a sketch of my graph. The other thing that's important with parametric equations, it's not a beautiful and perfect drawing, but it's a sketch. When we express our equations as parametric equations, this introduces an orientation. So as t increases from 0 to 2, how does x change? When t equals 0, x equals -1, and when t equals 2, x equals 1. So as t is increasing from 0 to 2, I'm moving along the curve this direction. So I'm moving along the curve that direction as the parameter increases. So parameterizing a curve introduces an orientation, introduces a direction that we're traveling along the curve. So we trace the curve from -1, 1 to 1, 1 as t increases. That make sense? All right, let's look at one that's a little more complicated. And these are the kinds of equations where it gets more fun. So we want to sketch the curve. We have x equals, here are parametric equations, x equals 5 sine theta, and y equals 3 cosine theta for 0 less than or equal to theta less than or equal to 2 pi. So if we want to, we'll get to the point where we recognize this graph, and we might be there already. So it's going to be an ellipse, right? How are we going to eliminate the parameter here to get a more familiar equation for this? Anybody have an idea? Let me do something with this. We could do that. Let's do something a little easier. Let me write this. X over 5 equals sine theta. Does that give anybody an idea? No, not triangles. Y over 3 equals cosine theta. Square both sides, because sine squared theta plus cosine squared theta is 1, always. So I can say that x over 5 squared plus y over 3 squared equals 1. So there's our ellipse. And so this ellipse, how are we going to sketch it? Where's the center? Our center is at 0, 0. It's not shifted. Major axis along the x-axis or along the y-axis? Major axis is horizontal. So here's my sketch. The major axis is how long? It's 10, right? It's 5 from the center on each side. So, and my minor axis is 6. So this is going to be a sketch of my ellipse. Not a beautiful sketch, but we get the idea. There's my ellipse. Use your imagination. Make it perfect. And as theta increases, from 0 to 2 pi, which direction are we going? So when theta equals 0, x equals 5 or 0. When theta equals 0, x equals 0, and y equals 3, right? So we're going to start, when theta equals 0, we start here, And when theta equals pi over 2, y equals 0, and x equals 5. So as theta increases, we're going around clockwise. So when we see sines and cosines, to eliminate our parameter, think sine squared theta plus cosine squared theta equals 1. That's usually usually a good place to start working when you have sines and cosines. You could get, you could work with inverse sines and inverse cosines. It just, your functions get a lot messier. So eliminating the parameter, mainly, the main reason we eliminate the parameter is to help with curve sketching. We want to be able to visualize what our curve looks like. We will do this enough that you'll get to the point where as soon as you see this, you'll recognize this as an ellipse with the major axis on horizontal. So we'll work with parametric equations enough that you'll be able to recognize what particular types of parametric equations look like without even eliminating the parameter, because we'll do this enough, we'll work with these enough that they will become very, very familiar. Any questions on what we talked about today? This is really all we're doing today. Just eliminate the parameter, know what a parametric equation is. So we're just going to practice with this. All right. Homework. There you go.